Well, now we will have the session 2, which will talk about image processing and artificial intelligent models. The first presenter of this session is Dr. Anton Vasiliuk. Paper ID is 343. Dr. Anton is a PhD student at Moscow Institute of Physics and Technology. He works at Artificial Intelligence Research Institute as a research engineer. His main research is safe utilization of computer vision models, and his speech title is Exploring Structure-Wise Uncertainty for 3D Medical Image Segmentation. Dr. Anton, please.
Thank you for the kind introduction. So yes, I can start. So yes, the topic of our paper was presented. So the structure of the presentation is going to be as following. Firstly, I will define what is structure-wise uncertainty and why do we study it. Secondly, I will show you define our experiments, how we start them, and the results will be on using structure-wise uncertainty for the quality control and its capability of false positive reduction, both on in distribution and the out of distribution data. So let's get started. How did we come to the structure-wise uncertainty? In medical imaging, it's common to provide a segmentation map for a problem. And when applying uncertainty estimation techniques for this task, they are commonly provide a whole uncertainty map. So it has quite a lot of information, and we are finding the best way to exploit this information for either false positive reduction or quality control setups.
Excuse me, sir. Excuse me. Could you share your screen? We cannot see your slides.
Oh, sorry very much. I was sure that.
Yes.
Yes, now you can see.
Yes,
right?
yes, right.
Hopefully that was no very important slides. The first one, the content of the presentation. I think I can not run it again. So the problem stated so that in medical imaging we got segmentation for many problems, and when applied uncertainty estimation techniques to this to the segmentation, they also produce segmentation uncertainty maps in some way. And we explore how to exploit these uncertainty maps to gain as much information from them as possible. And we use it both to reduce false positive predictions and to predict quality of different structures in it. And also in our study, we compare in distribution and the out of distribution performance. So what are previous work in this field? There is quite few works that explore such structure-wise uncertainty. The most notable one in false positive reduction is the works by Nevertol, in which they use some log aggregation for structures, while the other works work on crops of image or patches. And quality control, there is work by Roy-et-al, in which they estimate structure quality, but they're limited in the number of uncertainty techniques and uncertainty aggregation. And to the best of our knowledge, there is no work that compare in distribution and out distribution performance. So what is the framework of structure-wise uncertainty? The first step is to obtain predictions. Usually it's done with a single model or from different models. Having obtained a prediction, we separate it into individual structures, that is, connected components. And also we compute uncertainty map from single prediction or from different one. In the first step, we aggregate uncertainty map for a single structure and use this aggregated score either to reduce false positive predictions or for quality control purposes. So, each experiment, we find the optimal way to exploit structure-wise uncertainty. We are working with two sources of uncertainty. The first one is the magnitude of the output that is useful for a single model, or we use several different predictions. We study the several predictions obtained from ensemble, since the ensemble tends to produce the best quality uncertainty. But it's also common to use several predictions, for example, from Monte Carlo inference. For aggregation, we over a structure, we use mean, max, or mean values with the robust counterparts, that is 5/5 quantile, 9/5 quantile, and median value. And also we compare with the sum log aggregation that was mentioned in the work above. And for uncertainty estimation, we use just predicted probabilities or just sigmoid, the values of the network after sigmoid activation. We use also those values in the ordered space. We compare it with the entropy of output. We compare it with the average entropy over different predictions, with the mutual information, with the voxel-wise variance, and with the pairwise dice. That is just dice between different predictions for a given structure. So we have three different setups in our study. We use in-distribution data as a measure of systemic uncertainty, and the out-of-distribution data is a measure for relatoric uncertainty. So the first step, we train a model on dataset that has length cancer images, and compare this model when it's run on COVID-19 images. That was very important in the last years. The next setup, we train a model on liver tumor images from computer tomography images. And for OD data, we created an artificial dataset from the normal images in leads, in which we added typical computer tomography artifacts. And for the last setup, we work with MRI images, which we train model on a private dataset, which contains brain metastases that are in T1 modality. And for its OD counterpart, we use GD dataset that contains glioblastoma images in 4 different modalities. So as for the results, the first one is the false positive reduction, in which we measure how many fewer false positive predictions do we produce while obtaining a 95 recall value. So the baseline is just the output of a model. It is equivalent to the maximum value of given structure. And if we switch from the baseline to the mean entropy for structure, we can reduce the amount of false positive in 2 to 3% on average, and with even larger gain on individual datasets. But the more interesting part is that if we compare on ID data and OD data, the methods that we call discrepancy, it is mutual information, pairwise dice, and the variance. That is the methods that measure variance between different predictions. Then, even though they sometimes have worse performance or the same as the baseline or the entropy, the gain between OD data and the ID data is much larger. For example, Visual information is one of the worst performing methods on the ID data, but is one of the best performing on the out of distribution data. While pairwise dice is good on the ID data and the best method just on the OID data. This can also be observed from frog curves, where in the first row there is performance of the methods on the ID dataset, and in the second row the performance of them on the both dataset combined. We need to use both since there is no true positive predictions on the OID data, and there are these predictions only exist on the ID data. As for the quality estimation, here we plot dice score for a given structure with the value of structure-wise uncertainty. And as you can see from these figures, they are quite correlated. We also plot the linear model for just true positive predictions and the true positive and false positive combined. And the problem with this model dataset is that there are quite a few false positive predictions, and it affects the models quite a lot. So basically, one can use either mean predicted value or the mean entropy for the structure to estimate its quality. That is always better than use the maximum value of structure. And interestingly, for a single model, sometimes it has a more correlated values for true positive data than even an ensemble of models, but that's no longer holds true when added false positive data with a true positive. So, in conclusion, in this work we have shown that structure-wise uncertainty is a solid framework for both false positive reduction and quality estimation, since it requires little to no overhead over used machine learning models. It is applicable to any simulation models and allows for 3% reductions in false positive predictions and about 0.7 to 0.8 Spearman correlation with the object dice score. Mean entropy has shown to be the most consistent structural uncertainty method, and interestingly, on the out of distribution data, the discrete methods have shown to be much better than averaging methods with the pairwise dice showing the best performance. So thank you for your attention.
Okay, thanks, Dr. Anton, for your presentation. Are there any questions or concerns for Dr. Anton? Okay, thanks, Dr. Anton. And well, we will move to the next one.